Hey everyone, so today I'm going to finish the environmental toxicology notes, the part 2 version. Okay, so we're going to talk about detoxifying chemicals in the body. So I'm not going to click the present mode because there's no way for me to get the full screen into my video. Alright, so we're going to talk about detoxifying chemicals. So every day we're exposed to tons of different chemicals, and I know I said that before, and I really mean it. Like right now I'm sitting in my room here. I could be exposed to dust particles. I could be exposed to all kinds of air pollutants through the ventilation systems. So one major thing is, how does our body get rid of these chemicals? So one way that our body is going to get rid of these chemicals, if you were to ingest the chemical, or if you were, you're going to get it intravenously, like someone's going to inject you with the chemical. We use these detoxification enzymes, and they're known as cytochrome P450s. And cytochrome P450s, they're abbreviated CYPs, C-Y-P-S, if you look right here, CYPs. So there are millions of them, and they group them into different families. And the families are based on, what do they detoxify and stuff like that. So how do these things work? How do they make things more or less toxic and stuff like that? The first thing that they're going to do is they're going to go through this, what they call phase 1 of the detoxification. So phase 1 is going to involve where the cytochrome P450s, they try to add a hydroxyl group to it. So they add hydroxide, which is OH, and they're trying to make them more water soluble. And by making them more water soluble, they're going to be able to be excreted through your urine or through your sweat. So what happens is they try to add an OH group to whatever the chemical is, trying to make it more water soluble so you can excrete it through urine. If that does not work, then they're going to have to go to phase 2. And in phase 2, they're either going to add something like a sulfonyl group or an amide group or something like that. And eventually, if none of those work, they're just going to lock it up into your adipose or your fat tissue. Sometimes phase 1 detoxification can actually make something more toxic, which is really scary to think about because your body's trying to help you, but then it just kind of makes things worse. Alright, so here's the next one. Alright, so here are the cytochrome P450s in the human liver. So if you look here, these are the different families, and I just selected a few. Alright, so these substrates here in this column, this is going to be what they work on. Alright, so if you look here, ethanol is going to be alcohol. Let's see, caffeine is in here somewhere. Yep, there it is right there. So caffeine's right there. So CYP1A2 is going to metabolize caffeine. If you look over here in this column here, it's going to say genetic polymorphism. So there are genetic polymorphisms, which basically means that some people are better at metabolizing certain things than others. So it says 12% are poor metabolizers, for example. So 12% of people are pretty much resilient or resistant to caffeine. They ingest the caffeine like in a cup of coffee or something, and 12% of them actually don't even metabolize it, or they're poor metabolizers of it. So that's what the genetic polymorphism is going to mean. So again, there are different families or classes of these cytochrome P450s. Alright, so let's go on to the next slide. And this is showing you the different families. So it says major detoxification activities in drug metabolism. And it's a pie chart that's showing you different chemicals and which families they are associated with. Alright, so if you look over here, ibuprofen is down here with CYP2C9. Up here we've got caffeine, we've got diazepam, omeprazole. So there's tons of different families or classes of these cytochrome P450s or these CYPs, and that's how your body is going to try to detoxify things. Alright, so let's talk about toxicity testing standards. So back in the day, back in the 1960s and the 1970s, people were really obsessed with these toxic chemicals because remember Rachel Carson's book, Silent Spring, and all those different things. Those were basically saying, okay, these chemicals are toxic, we're being exposed to them, how much is too much, and shouldn't the government be regulating what we're being exposed to, right? So the EPA came up with TSCA, which stands for the Toxic Substances Control Act, and that was in 1976, and that gave the EPA the power to regulate tons of different chemicals. It's going to exclude food and cosmetics. That is going to be the Food and Drug Administration, which is the FDA. And then pesticides are going to be regulated underneath FIFRA, which is the next law that I'll talk about. So TSCA is 1976, Toxic Substances Control Act. All right, the next one we're going to talk about is known as FIFRA, the Federal Insecticide, Fungicide, and Rodenticide Act. And I put 1996 here because this is the last time that it has been amended. So it was created around the same time as this Toxic Substances Control Act, or TSCA, but it was amended in 1996. So underneath this this act, pesticide creators and manufacturers of different pesticides, they have a legal right or a legal responsibility to show that a pesticide will not cause unreasonable adverse effects on the environment. So what it forces the companies to do, the manufacturers to do, is to do these bioassay tests. And they're going to do the bioassay test on things, it makes them do it on a bird, a mammal, a fish, and an invertebrate. So usually the bird is going to be some sort of like a blue jay or a crow or something like that, something that's a really common bird. The mammal most of the time is going to be a lab rat or some sort of mouse or mice. The fish most of the time is going to be a bass, steelhead trout. That's really pretty much it for those. And then the invertebrates are going to be brine shrimp most of the time. Or sometimes they'll use these things called water fleas, which they're not fleas at all. It's just Daphnia. That's the name of these things. So some people may have noticed, they said, okay, well, why aren't amphibians and reptiles included? Because back in the day, no one really cared about them. And they said, it's fine. They'll be fine. Actually, they weren't. If you know the herbicide Roundup, Roundup has been linked to thin skin thickening and other things in amphibians, and it's killing a lot of amphibians like frogs. Alright, so I'm going to delete this picture. So doesn't it sound strange that humans test chemicals on rats and then they extrapolate that data to humans? So the word extrapolate is going to mean, okay, so we have this data and we're going to take it and we're going to extend it outwards. So for example, if we have two variables and we see that there's a trend between the two, we can take that and extend it outwards for other things. So we can't do dose response tests on humans or apes because they have the ability to throw up. They have the ability to realize that they are being poisoned. So they'll either stop taking it or they'll start to throw up and stuff like that. So what they do is they take the LD50 or the ED50, remember lethal dose that kills 50% of the population, or the effective dose that kills 50% of the population, or harms, or whatever. Those values are determined for rats, and then they divide them by 1,000 to get that value for humans. So this is just trying to guarantee additional levels of protection for humans, but it does seem strange because, you know, rats are not humans, and humans probably metabolize things differently than rats do. So here are the different categories of chemical hazards. So the first one we've got here is mutagens, and mutagens are things that are going to mutate your DNA. Most of the time they form these things called DNA adducts, which I'll explain here in a second. Carcinogens, which are things that cause cancer. Teratogens, which you may not have heard of. So teratogens are things that cause birth defects. Neurotoxins we've talked about neurotoxins before in the form of lead and mercury and stuff like that. We'll also talk about some insecticides, allergens, which you've heard of, and then endocrine disruptors. Alright, so let's talk about mutagens and carcinogens. So carcinogens are chemicals that are going to cause cancer, and most of the time they do so in a way that causes cell damage, and it harms the ability of your cells to regulate their growth. So remember in biology when you talked about, you know, the cell cycle, and then the cell cycle got out of control and all that kind of stuff. Those are all things that these chemicals can cause. They can cause some sort of uncontrolled cell growth, which can then lead to things like tumors and metastatic tumors. And metastatic tumors are just tumors that will spread from one part of your body to the other. So here's some examples. I don't know why I have radon twice. Asbestos, remember those things were, this will get into your lungs, so those long, thick fibers that were in like ceiling tiles during the 1970s. Radon is coming from the radioactive decay of uranium in your basement. Formaldehyde, those are, that's a VOC. Benzoylpyrene, both of these are from tobacco smoke, so if your parents smoke inside, you're probably going to be exposed to a lot of these chemicals. And then finally, we're going to talk about carcinogens. So carcinogens, mutagens. So mutagens, they are going to cause these things called DNA adducts. And adducts is spelled ADDUCTS. So what happens is something like a synthetic chemical like PCBs, and PCBs are polychlorinated biphenyls. They used to be like an industrial solvent kind of thing, so they would grease the gears really well. They're found in Lake Hartwell. The fish in Lake Hartwell have PCB contamination in them as well. So what happens is the PCBs, or the chemical, is going to bind itself to your DNA. And when I say it binds itself to your DNA, it forms these things called adducts. So since the chemical is like stuck on your DNA, whenever DNA polymerase tries to go in there and it tries to read your DNA to either replicate it or fix some errors or something like that, it can't really get over the adduct that's formed, and it's just kind of stuck. So if this is like reading your DNA like this, it goes across, and it kind of gets stuck here because there's this giant molecule here sitting here, and it just runs into it and it can't get around it, which can then cause mutations and things like that. Alright, so let's talk about this, and I'll delete these pictures, and I'll talk about them here in a second. So teratogens are things that are going to affect the development of a fetus or the development of an embryo. So one of the most common ones that people always talk about is alcohol. So if you are pregnant, or your wife is pregnant and she drinks excessive amounts of alcohol, it can lead to this thing called fetal alcohol syndrome, which is really bad for your baby's brain. And your baby will probably be born with a lowered IQ, or possibly mental retardation if you're exposing your baby to that much alcohol. So this alcohol, you drink it while you're pregnant, and then it concentrates itself. It damages your baby's brain. So one of the most famous teratogens that people always talk about is this thing called thalidomide. And thalidomide was prescribed to pregnant women during the 1950s. Most of the time it was prescribed in Europe, more specifically Germany, and then it was also prescribed to some women in Latin America and the United States. So it was used to treat morning sickness, but then people realized that it wasn't actually treating morning sickness. I mean, it was, but then when their babies were born, they had malformed limbs. So I'm talking about enantiomers here. So this word here, enantiomer. So enantiomers in organic chemistry, there are two different versions of basically the same model, and they call them the right-handed model and the left-handed model. So they always say it's like your hands, right? So your hands are non-superimposable mirror images, right? So if you try to flip this one and then put it on this one, it doesn't match, exactly, kind of thing. They're non-superimposable mirror images. So there are two enantiomers of most organic molecules. So for example, chocolate. One enantiomer is the chocolate that you know and love. The other one is a highly potent poison. So there are two enantiomers of the thalidomide. Let's say the left-handed one is harmless. The other one is a teratogen. And those pictures that I showed you earlier, so these pictures here, these are showing you kids that were exposed to thalidomide as a child. So if you look, this kid here, his mother was exposed to thalidomide, and these other kids over here weren't, and it's really sad. Let's move on and talk about neurotoxins. So neurotoxins are any chemical that's going to disrupt your nervous system or your neurological system. So you could be talking about your brain, you could be talking about nerve impulses, stuff like that. Insecticides are also neurotoxins, and I'll talk more about this here in a second. Lead and mercury are common heavy metal neurotoxins, so they make you forgetful, confused, and all kinds of stuff like that. Lead contamination in the United States is a really big problem still, and most of this is in the form of water. A lot of pipes are made out of lead, so then the water slowly eats away at the lead, and then you get lead into your drinking water. It's a really big problem for kids. Flint, Michigan is a prime example. So insecticides are also neurotoxins, and most of them are these things called acetylcholinesterase inhibitors. All right. So acetylcholinesterase, this is an enzyme, and the enzyme is going to break down this thing called acetylcholine. All right. So acetylcholine is a neurotransmitter. So a neurotransmitter is a molecule or a compound that goes across the synapse, and I'll show you a picture. I've got a picture here in a second. Across the synapse to transmit a message. All right, so I drew this picture, and I know it's kind of terrible. All right, so if you look at this picture here, all right, this here is going to be the end of one neuron, and this over here is going to be the end of another neuron. All right, in order for a nerve impulse to go from one to another, you have to have a neurotransmitter, such as these little circles in here, and they have to go across this space in the middle, which is called the synapse. All right, so there's a space, like super tiny space, in between these neurons, and the neurotransmitters go across the space to transmit a message. But whenever these neurotransmitters get over here, they land here, and they have to be degraded somehow, or else the nerve response never stops. So that's what these acetylcholinesterase inhibitors are doing. They're preventing the breakdown of acetylcholine, or these neurotransmitters. Alright, so let's talk about some common insecticides in America. Alright, so these are listed in order that they were created. Alright, so before organophosphates, there were organochlorines, and organochlorines are things like DDT. Alright, so they work as these acetylcholinesterase inhibitors, so the picture that I just showed you, where it prevents the breakdown of that neurotransmitter, that acetylcholine, and since it never breaks down, the nerve impulse just continues and continues and continues until it basically kills you. Alright, so sarin gas is an example of an organophosphate that was used on humans. This was used in Syria recently. It was outlawed as a result of the Geneva Conference, after World War II, but Syria still used it on its own people during the Syrian Civil War a couple of years ago. So sarin gas, what it does is it causes the same thing that it would in you as it does in insects. And the symptoms are going to be, you'll feel like chest tightness, wheezing, pulmonary edema, and basically what it's doing is it's trying to paralyze your lungs. Eventually it leads to seizures, lack of consciousness, and then respiratory failure. So what happens in humans is if you're exposed to this and you can get yourself to a hospital, or someone will take you to the hospital, they could administer this drug called atropine, which is atropine, I'm assuming. So atropine can be administered through an IV or through like an injection, and that will bind up all of your acetylcholine, so then the organophosphates will just be flushed out of your system. Alright, so the next one are called carbamates, and carbamates are derived from carbamic acid. I always mispronounce that. They kill the insects the same way. So they are, again, they're these acetylcholinesterase inhibitors. They're not very toxic to mammals, though. For some reason, mammals don't have the same capacity as others do. The most common one of this one is called 7-dust, and it's spelled exactly like this. That's why I put the registered trademark here. So 7-dust is like a powder that you would throw out around your yard. I think you can still buy it at Ace Hardware or some other hardware store, and you just throw it out and it deters pests. Pyrethroids, these are the ones that are like the wave of the future. So what they've done is they found these pyrethrins that are found in chrysanthemum plants, and they are a natural insect repellent, and the plant just produces them naturally. So what they've done is they've taken these pyrethrins, chemically altered them, and changed them into pyrethroids, and these are synthetic pesticides that they basically have the same properties as pyrethrins. And how these work is they affect the sodium channels in the axon. So if you know anything about anatomy or physiology or anything like that, maybe if you're in Miss White's class, you know that as the sodium-potassium pump, the sodium it goes in and the potassium comes out. Well, the sodium channels really never close here, so it causes a rush of sodium into your cells, and then the action potential never ends, basically. All right. So here are allergens. Allergens are, everyone knows what an allergen is, but some people don't realize what actually happens in your body whenever you have an allergic reaction. So what your body does is your body is exposed to some chemical, and then it elicits an immune response by your body. So when I say immune response, your immune system thinks that this allergen or this chemical is some foreign invader. So what it does is it tries to basically add antibodies and antigens to it to slow it down so it can kill it. And this whole immune response is detailed in this picture here, where you basically are exposed to some allergen. B cells are a type of immune cell in your body. They make these antibodies, and the antibodies attach themselves to this mast cell. And then as your body slows down the allergen, your body then releases this chemical called histamine. And histamine is going to be the one that makes your nose runny, makes you like cough and all that kind of stuff. Because what your immune system is trying to do is it's trying to get you to get rid of this allergen. Because it thinks that it's some sort of outside chemical invader. So if you take Benadryl is an antihistamine, and antihistamine is just going to block your response to that histamine that's being released by your body. So common allergies are peanuts, mold, penicillin, codeine, pollen, mold. So there are tons of different things. Some immune responses are extremely intense. Some are very small, like hives, sneezing, watery eyes, but some are, they cause this thing called anaphylactic shock. And anaphylactic shock is going to be where your body, your throat swells up, and then you can suffocate. All right, so endocrine disruptors. Endocrine disruptors are chemicals that are in your body that look like hormones, but they're not. They have very similar structures to these hormones, and they block a message. So what it does is these hormones attach themselves to a receptor, and this is what happens normally. Let's say that there's some hormone, it binds to this receptor on your cell, and then it elicits some sort of response. But then, if we've got this endocrine disruptor over here, the endocrine disruptor looks exactly like this hormone, but it's not. And it blocks the receptor here, and there's no way for the response to be received. So an example of this is 19-beta-ethinyl estradiol, and it basically is birth control for women. And it's found in wastewater and all kinds of stuff like that. And male fish, amphibians, and reptiles are all becoming feminized, and it's leading to them developing eggs, which is going to raise serious concerns in the future, I believe, about male fertility and things like that. All right, so then finally we've got these emerging contaminants. And we've already talked about emerging contaminants like caffeine and ibuprofen and acetaminophen. And what happens is you ingest them. Your body doesn't metabolize 100% of them. You excrete a small amount of them in your urine, and then the wastewater treatment plant doesn't really have a way to get rid of those. So what it does is it actually just excretes them, or it just moves them right through, and then they put them into natural waters like a lake or something like that. Remember that giant chart that I made you do where it was like, oh, there's all these chemicals in the water, and you could be drinking them, and that kind of thing. And then finally, there was the whole study about Prozac that I did in the previous video where they they increased dosage of Prozac or fluoxetine to those bass, and the bass eventually just started to ignore their prey, and then they starved to death. Alright, so I've tried to keep this video to 25 minutes. If you haven't noticed, I've been speeding up the past couple of slides because there's a countdown clocker or ticker down here in the bottom. If you have any questions, please let me know. Comment if you like this video. Shameless plug here. Follow me all and subscribe to my YouTube channel. Have a great day.